Okay, hello everyone. Today we will continue working on the equilibrium. And first we're gonna talk about some graphs. So as you can see, this is the concentration of each substance. And sometimes you're gonna see like a peak, okay, like a peak, and it goes up or goes down. And the new equilibrium will be established. For example, this one you insert more carbon monoxide, and when was the stress applied is 20 seconds, and which direction is it going to be shifting. So there's more carbon monoxide on this side, and it's going to shift to the right to balance. And this one changing in the temperature, so this one, what direction does it change? Okay, so we can see there's like straight lines here, right? That means it was like equilibrium until there's some change of the temperature. And we can see the CO and the Cl2, they are kind of getting lower and lower, and this thing is getting more. Therefore, this thing is going to be shifting to the right. And based on like this is a exothermic reaction, therefore, so if increase of this heat is going to shift to this side to favor the endothermic. If I lower this one, this is going to shift to the right and favor the exothermic. Therefore, this is cooling. And the volume and the pressure change. So this one, we can see this like a spike, and the CO2 are going down, and the Cl2 is also going down, and that means this is a right shift, which means there should be a increase in pressure, and this leads to the reducing of the volume, and those molecules, they are becoming less amount compared to before and after, because originally I have those two moles of substance and they kind of combine into one mole, and that corresponding to the reducing of the volume. And when we are talking about this, we are always talking about the gas, because liquid and solid, they are not going to change their volume. Okay, we learned the equilibrium constant. So the K is going to be, if we have something like this is going to be the concentration to the power of coefficient of the products over the reactants. And this will be experimentally discovered, just like the rate law, okay? It is also known as the law of mass action. And write this. So this is what we assume by default. So this is the product, and then we take the concentration of the product and each raised with the coefficient at the front, and we divide it by the product of the concentration of the reactants to raise to the power of their coefficient. And we have also a lot of different subscripts, like C stands for concentration, EQ stands for equilibrium, and A, B stands for acid and the base, and there's a lot of those things, but it is always it is always the product over the reactant. Okay, so relationship between Q and K. So Q is at any time the quantity of the ratio of the concentration of product over reactant, and K is the constant where this ratio reach the equilibrium. And if Q is less than K, then there's a right shift because there's less product and more reactant is going to form more product, which is the right shift. And if Q is greater than K, that means there's more product than reactants. Therefore, the product will be converted back to the reactant. And as you can see, we just don't care about the solid. We don't take that into account because the volume of that is not going to change at all. So it doesn't matter. We only care about gases and liquids actually. Like this is not liquid. Sorry, this is the aqueous. And yeah, just the same trick here. And if we change the coefficient, if we multiply like both sides by a certain number, and we're gonna raise the original equilibrium constant to the power of that number. And if we reverse it, we're gonna take the inverse of the number. If we add two different equations, we multiply the constant. And if K is greater than 1, that we call that this is product favorable because there's more product compared to the reactant at equilibrium state. If this is less than 1, it's the opposite. We say this is reactant favorable because there's more reactant. And there's some example problems. For example, this one, we are given those concentrations, so we get the equilibrium constant formula, and we sub in and we calculate the K. And sometimes you need to solve like a equation. For example, this one, we know the concentration of the original all three substance. And at equilibrium, we find NO2, and we solve the rest of the ice table values, and we sub in the final equilibrium concentration into the formula, and we get a K. And sometimes the things are getting much more complicated, where you need to solve like a quadratic equation. So for example, this one, we are known the original concentration, and we know the value of K. And we need to use the stoichiometry ratio and use that to obtain the new set of concentration of the product. After you sub in those different x's, and you're gonna have this equation, and you're gonna solve the quadratic and solve the value of x, and you sub in back to the final numbers of those concentration, reactants, and products. And this one is also very special, where you kind of add more to it. First we calculate the equilibrium constant of K, because originally this is at equilibrium state, and then we add some kind of water, some amount of water. And we know that the final equilibrium state has 0.77 m of hydrogen, okay? And we know how much is this changed by, except this one we added some unknown amount of water. And we obtain and we use those four to make an equation with K, and we solve for W, and we know the concentration. And one thing to mention is that if this K is extremely small, and you can just ignore like subtraction and addition. And is this going to shift right or left? So how we determine this is by observing the relationship between Q and K. As we can see, this one, the Q equals to 1.5, which means it is less than K, which means there are less products and there's more reactants, so we're gonna shift to the right to produce more product, okay? And yeah, that's pretty much what we learned yesterday. Thank you for watching, and see you in the next one.